Good afternoon. A very warm welcome to all of you who are joining us through this webinar. And I'm delighted to welcome Professor S. Gurubaran, the speaker for today's colloquium, who is a PRL alumni, and he has kindly accepted to give this colloquium for us today. Professor Gurubaran, as I said, he's did his PhD from PRL 93. And after a couple of years of postdoctoral work here at PRL, he was a postdoctoral fellow at the NCAR High Altitude Observatory and associate visiting professor at RISH, that is Research Institute for Sustainable Humanosphere at Kyoto University in Japan, for about 8 months. His main fields of research are dynamical coupling of atmospheric regions and electrodynamics of equatorial ionosphere. He has over 100 publications to his credit, and he has guided more than 10 PhD scholars. Internationally, he was also responsibilities-wise, he was also elected as the chairman of the Interdivisional Commission for Developing Country, which is a part of IAGA, International Association for Geomagnetism and Aeronomy, and he has his main presently he's working as a professor at the Indian Institute of Geomagnetism, and I had known him right from the days of our PhD time. He is a very active researcher, an expert in various analysis methods and also experimental techniques. And it's from higher altitude in F region ionospheric research. He moved to slightly lower below, but then he is involved in various research using various types of experiments, instruments, and also some of simulation works. It's always a pleasure to interact with him. And with this, few words, I will now request Professor Gurubaran to commence his colloquium on a very interesting topic of internal bores in the mesosphere. And we'll hear more about it today. Guru, please. Over to you.
Thank you. Thank you, Professor Pallamraju, for your very kind words. And I am happy to be here as alumnus, one of the alumni of PRL. And also glad to see all of you here. And maybe I'm giving this colloquium after maybe 10 years. I don't remember when I gave a colloquium last time.
Yeah.
And I'm very happy to be here today. I'll share my screen now.
Yes, please.
You're able to, I think.
Yes, it's coming. Yes.
Yeah, I think now it's coming now.
Can you make full screen and also that hide bar at that bottom?
I'll hide that. Yeah.
And we can use the pointer also.
Yeah, it's fine, right?
Yes, it's fine. Now you're able to see.
You're able to see the screen, no? Full screen? Yep.
Yes.
Yeah.
Yes.
So this is a topic which was motivated by one of recent works that I and my student Nilesh carried out based on all-sky airglow imaging observations from Silchar. Though my past work goes back to 2008, 2009, along with my earlier student, Lakshmi Narayanan. But the present observations were quite interesting, and I thought we should revisit the mesospheric bores and see what we can do further. So because this is an area where not many people would know. So I thought I'll give a good introduction about what are bores. I'll start with atmosphere, the dynamics, waves, and then the conditions required for the propagation of the mesospheric bore. This is just a picture which shows a surfer riding over a bore tide on Turnagain Arm. Okay? This is in a gulf in Alaska, and it's a very narrow channel. Water rushes through the channel and then goes into the sea. And then there is a return flow because of the faster velocities and the piling up of the mass. Then there is a return flow that I'm going to cover. I'm going to talk about that a little later. It's a very beautiful picture of a tidal bore. I thought I should share it here. Before I go into my topic, I would like to give a flavor of where I am from, about my institute, what we are doing there, maybe just a slide or so. I am from Indian Institute of Geomagnetism. So this is a autonomous research organization under Department of Science and Technology, Ministry of Science and Technology. And as you see, it has a true pan-India presence. We have magnetic observatories starting all the way from Gulmarg to down south to Tirunelveli, and from west to Rajkot to Silchar and Port Blair on the east. By the way, we do carry out fundamental research on geomagnetism. Essentially use geomagnetic measurements as diagnostic probes to study and understand our near space environment. To understand the space weather, there is the weather of the near space environment, then the particles and radiation entering into the atmosphere and the ionosphere, and the changes take place there in the space environment. That is our focus. So we have magnetic observatories, and then we have several radio and optical remote sensing tools to probe and understand this environment. So we have a rich legacy. It's about 175 years of legacy on continuous geomagnetic field measurements. It all started in 1841 at Colaba at Bombay. It was known as Colaba Observatory, and then we moved on to Alibag in the early 20th century. And we have this Colaba Alibag Observatory. It's operational since then. A continuous, more than 175 years continuous observations. The institute itself, it was carved out of India Meteorological Department in 1971 with a mandate to conduct research in the geomagnetism and allied fields. So we have 3 regional centers, Tirunelveli, Allahabad, and Shillong, and 12 observatories in India. And also we have observatories in Antarctica, to where our colleagues, they go on Antarctic expeditions every year. We have observatories at Maitri and Bharati in Antarctica. There are 3 research divisions broadly: observatories and data processing, upper atmospheric studies, and solid earth studies. Though, of course, we do a lot of interdisciplinary work. There is a cross-cutting across disciplines and exchange of ideas and all that. Because when we talk about earth system science, it's all the various domains that are coupled together. And so it's one of the very unique institutions in the country that have scientists from space, atmosphere, and earth sciences. There are major scientific programs, 9 scientific programs with strong traditional participation. And as I was telling, from space weather to geophysical processes interior to the Earth, IAG is involved in a very unique blend of research areas, cutting across disciplines like plasma physics, atmospheric ionospheric physics, geophysics, geology, and even there are even applied mathematicians too in our institute. With that background about my institute, I will move on to the topic of today's discussion, that is bores, internal bores in the mesosphere. This is not a new topic, by the way. Bores have been known for quite some time to occur. For example, there are the channel bores and estuaries and rivers where there is a narrow shallow water, a narrow width, water rushing into the sea and then emptying the water, and then there is a piling up of the mass, and then there is a pressure gradient there, and there is a return flow. Okay, so, and even in the lower atmosphere, bores have been known to occur. I will mention about that a little later. So it's a kind of disturbance in the atmosphere having their origins. For example, I was telling you the lower atmosphere, so cold front intrusion into a stable region. We can also have convective outflows and gravity waves. Of course, higher up into if you go higher up into the atmosphere, gravity waves are believed to be a major source of bore generation. In all these bore phenomena, we need a stable atmosphere, a region where the atmosphere is more stable, and below which or inside which we can have some kind of a ducting, and the bores can propagate. I will talk about that a little later. And when it comes to the lower atmosphere, the temperature inversion, where the temperature, instead of decreasing with altitude, the temperature increases with altitude, we call that as an inversion layer. That's a stable region. And so a cold front or a convective outflow applying any kind of disturbance there, that can be confined in that, and then the bores can be generated, they can propagate. I will come to that a little later when I discuss about the idea behind the hydraulic jump. Yes, so much of the theories utilize the concept of hydraulic jump used in tidal bores occurring in rivers and estuaries. So as I was telling, essentially it is a shallow water with a narrow width, water entering into an ocean. Then it's a piling up of the mass there, and then there is a return flow. You can even if you had seen in your toilet sink, when you open the tap, water just comes out, right? And then you see that there's fast-moving water coming out, and then you see surrounding the edges there are water is still there. So there is a discontinuity in velocity and therefore the pressure, and you see that the water spills surrounding that. You see there is a slight jump there in the fluid, across which there is a steep discontinuity in the velocity and the pressure. So this is an analogy given for in terms of the hydraulic jump theory. So as I was telling you, the bores need a stable region. For example, temperature inversion is one region where the air masses can have kind of a stability. I will talk about that a little later, and so they can propagate in that region. So to understand mesospheric bores, I think it's very important to know about the atmospheric waves, because that is a fundamental thing that the agency is going to generate bores in the mesosphere. So a little background about what are atmospheric waves and what do they do in the atmosphere, why they are important, and what is the connection between these waves and the bores high up in the atmosphere. So you can imagine from analytical ideas, essentially the atmospheric waves are the perturbations over zonal mean state of the atmosphere. So in various spatial and temporal scales. So usually when you talk about the mean state of the atmosphere, essentially it is a zonal mean. That is, you take the average of the parameters like temperature, range, densities across all longitudes. Then we call that as a zonal mean state of the atmosphere, as a zonal mean wind, or the zonal mean, zonal wind, zonal mean temperature, zonal mean densities, and so on. If you consider the zonal mean state of the atmosphere as a zeroth order state, then the waves can be considered as the first or second order terms in any linearized set of equations. Okay? So they are the perturbations over the zonal mean state of the atmosphere. These perturbations can have periodicities ranging from, say, a few minutes. It's called the buoyancy period or Brent-Weisel period. I will come to that in a moment. To the several days in terms of spatial scales, and in terms of temporal scales, few minutes in terms of in time, to several days for the planetary scale waves. And when it comes to spatial scales, so it can be a few tens of meters, just above the turbulent regime, and then all the way to the planetary scale. That is, if you take the circumference of the globe as 40,000 kilometers, that could be the largest scale which these waves can, occur. So a variety of spatial and temporal scales over which these waves can occur. The waves presence can be seen. So this shows the zonal mean state of the atmosphere. I think I'll have the laser pointer here. Yeah. On this side we have the temperature. On this side we have the zonal mean. And to begin with, we have the solar radiation entering the atmosphere, and the radiation is absorbed by gaseous species, various atoms and molecules. And then the excess radiation, or whatever radiation is absorbed, can be partly realized as heat. And also part of the radiation escapes the gases emit radiation, and that can escape into the atmosphere. Also possible that the energy quanta, they are transported from one place to another. So we have the solar insolation, that is absorption of solar radiation. Then there is the emission of radiation by atmospheric gases, as well as you have the transport, right? Transport of heat. So we have the energy equation based on the first law of thermodynamics. Then there will be a forcing term on one side, and then we have production loss and transport terms on the other side. The temperature profile is largely determined by the solar radiation absorption. But there is a slight imbalance between the amount of radiation absorbed and the amount of radiation emitted, and that's what determines the thermal state of the atmosphere. So if you go from ground, we have the troposphere, stratosphere, and the mesosphere. And the stratosphere is a region where the large amount of solar radiation is absorbed, and because of the presence of ozone there, the temperature shows a large value. Temperature shows a maximum, in fact. So it's about 300 K, close to 300 K in the stratosphere. But then if you go up into the mesosphere, very little solar radiation is absorbed there. Okay, but there is a lot of cooling is taking place. So this cooling plus reduced solar absorption, it leads to reduced temperatures there in the lower temperatures there in the mesosphere. If you observe these contours carefully, see when you go from summer to winter, you see the summer stratosphere is warmer than the winter stratosphere. That's fine because of the presence of absorption of solar radiation there. But when you go up into the mesosphere, you find that the summer mesosphere is cooler than the winter mesosphere. That means the summer there is cold compared to winter there. Okay. So as I was telling you, we have to take into account the competition, the balance between the three terms, production, loss, and the transport. And because loss being significant there, so whatever energy is absorbed or whatever energy is released as heat, that is now emitted by a species and it escapes into space. So we have reduced temperatures there at the summertime. On the other hand, on the winter, though the same situation does arise, but it is expected that a lot of wave activity happens there in the winter mesosphere when compared to summer. And these waves, especially the planetary scale waves, so and also partly gravity waves, when they break, they deposit their energy and momentum, and they contribute to heating there. I am going to talk about that a little later. So, because the winter is somewhat dynamically active, so we expect that the winter mesosphere, it will be somewhat warmer than the summer being very quiet there. When it comes to the zonal wind, you see these easterlies and westerlies. Easterlies in the summer hemisphere and the westerlies in the winter hemisphere. They characterize the wind system of the middle atmosphere. So this represents the background state of the atmosphere, the zonal mean state of the atmosphere, because this is very important when we discuss about mesospheric bores. because the background temperatures and winds play a very important role in determining what waves can propagate, what waves can be filtered out, and what waves can enter into altitudes like 80, 90 kilometers, and they can produce those effects that I'm going to discuss now. So it's just not simple radiative equilibrium model, especially when it comes to the mesosphere. Dynamics there plays a very, very important role there in the mesosphere. And wave dynamics actually, in fact, can explain why summer mesosphere is colder there. Atmospheric waves are essentially, when it comes to atmospheric waves, an important dynamical property of the atmosphere is to support wave motions. Essentially, we need to keep in mind the atmosphere can be considered as a stably stratified fluid. So we have a stable density stratification. The density exponentially decreases with altitude. And so if we try to lift an air parcel, an air mass, what's going to happen is when it is lifted up, it will feel itself heavier than the surroundings and it is going to sink back. And then when it comes down and it overshoots its initial position and goes below, then it will find itself lighter than the surroundings. So positive buoyancy, right? And then it is going to move up. So if you give a slight push and leave an air mass, so what you would expect is some kind of a buoyancy oscillations. These air parcel or air mass will undergo. This is the basic facet of the buoyancy waves or the gravity waves that I'm going to discuss about now. Okay. And because it is stably stratified, you have this kind of up and down motions can take place there. A sinusoidal kind of an oscillations, stable oscillations can occur there. And because there is no boundaries, no upper or lower leads, there is no enclosures, these waves can propagate in all directions. They can propagate up, they can propagate down, they can move sideways. And remember, these are all essentially transverse waves, unlike sound waves that are longitudinal waves. The restoring forces are essentially, as I was telling, the density, stable density stratification, buoyancy in one side, and the positive and the negative buoyancy. Okay, and gravity playing a supporting role there. And when it comes to very large scale sizes, the Earth's rotation, the Earth's sphericity, they all will come into the picture. And so the Coriolis effect plays an important role for large scale waves. And because the Coriolis effect varies with latitude, so that plays acts as a resistance for some of the large scale planetary waves. Essentially, atmospheric waves can be considered as a linearized disturbance to the basic state, and the basic state it can be at rest or it can be moving. And based on that, restoring forces. So small scale waves, they come under the category of internal gravity waves or buoyancy waves that owe their existence to stratification. Then we have inertia gravity waves, the combination of stratification and Coriolis effects. And finally, planetary waves or Rossby waves, which essentially comes from the Coriolis effect. Now, these waves can be either forced or they can be natural modes of oscillation, resonant kind of oscillations. They can be there all the time. If not, then these oscillations can be forced at some lower boundary. For example, convective overshoot, no? When we have a very strong intense convection, air mass entering into the upper troposphere, there can be a forcing for a gravity wave. Not only mechanical, it could be thermal also, because the air masses carrying water vapor, when they condense, they release, carrying moisture in it, they condense, they release water vapor in it. So there is a conversion of, there is a release of latent heat into the system. So that can be a source of energy, and that can excite waves, small scale waves or even medium scale waves. And we can also have topographic contributions, orography. We have mountain, we could have land, ocean. So the thermal contrast between these topographic or orographic features, they can also excite waves. Right? These waves can propagate up into the atmosphere. They can be trapped or evanescent. It's also a very important aspect of wave dynamics. Waves can either propagate, then we call them as internal waves. Then the waves can get trapped close to the source region, they become evanescent. That means their amplitudes decay very steeply. And we call them as external waves. I think I have one slide that shows the difference between these two, internal and the external waves. Okay. Waves can be stationary waves or traveling waves. If I say stationary waves, the wave fronts, no, they need not move. They can be just fixed in space. And just a time varying feature that we observe from ground. Or they could be traveling waves. That means when the wave fronts, they can be moving in space, and we call them as traveling waves. Most of the waves that I'm going to discuss, they all belong to the category of traveling waves. A very important feature is whether these waves undergo mean flow interactions. It's not just that the waves are excited, the waves are generated, and they propagate. There's also, remember, the background atmosphere. The background is not going to be at rest. So I showed you the zonal mean state of the atmosphere. No? Continuous, the winds are blowing there. Day-night winds, then seasonal winds. So winds of all kinds, no? They are blowing there. Trade winds, easterly winds, can also have westerly winds, and so on. So these waves, no, they can interact with the background wind. So because we are observing, we are looking at the atmosphere from the ground, and we are observing wind as well. What happens is these waves undergo some kind of a frequency shift, okay? Or we can call that as a Doppler shift. So the frequencies can increase or decrease depending on whether the winds are blowing in the same direction as the wave front motion, or the winds are blowing in the opposite direction. The winds are blowing orthogonal to the phase motion, absolutely no issue. We don't have any problem. So we need to consider a component of the wind that blows in the same direction as the direction of the phase motion. Okay, that's a very important aspect. As I was telling you, the waves get Doppler shifted and all that. Okay, and the waves can slow down as they approach a critical level, and then the waves can get absorbed. Okay, so these are a couple of things which I am going to discuss. I think I will be discussing later. I will not go deep into that now. So what is the starting point for analyzing linearized disturbances to steady flow? Of course, the set of primitive equations, the conservation laws, momentum, mass, and energy. This is a very generalized expression taking into account the spherical Earth, the Coriolis effect, and the various momentum and heat sources. X dash, Y dash, they are the momentum sources, and J dash is the heat source. And we have these three sets of equations, a very complicated set of equations, and they have to be closed. And we also have ideal gas law, an equation of state. And then, of course, we also have the hydrostatic equation. These are the sort of closed system of equations, and we can try to solve these equations and get the U dash, V dash, W dash, whatever it is, perturbation terms. So when we examine planetary scale oscillations, it's very useful to separate them into latitude and height dependencies. Then we can write these perturbation terms as separately as latitude term, longitude term, and space and time. Then we also have this e power z by 2h. So that indicates the exponential growth of these wave amplitudes, because the densities are decreasing with altitude. So in order to conserve the kinetic energy density, we expect the wave amplitudes to grow with height. Okay? And so that term represents the wave growth with altitude. Okay? Of course, the waves do not grow indefinitely. I will come to that in a moment. Waves undergo damping, waves can get dissipated, waves can undergo instabilities. The waves can get filtered out, okay? Waves can interact with the mean flow. There are many, many things happen to these upward propagating waves. Okay? So the spectrum of waves that is generated somewhere lower below, that will be somewhat different from what we observe in the mesosphere, lower thermosphere region. you would find that many of these small-scale waves they've all been filtered out, and what we are left with is medium to large-scale waves. But it might also happen that when small-scale waves, when they dissipate, when they break, they can induce some kind of a mean flow acceleration, and that can give rise to secondary wave generation. These secondary waves can, of course, propagate up. They can have their own interaction mechanisms with the background flow and so on. So, so we will not go into the Laplace tidal equation, the vertical structure equation, because they're all important for analyzing planetary scale oscillations. What we will confine ourselves is to the small scale oscillations, for which the Earth's rotation and the sphericity do not play any role. And we all been hearing that gravity waves are ubiquitous in nature. They are there all the time. In fact, meteorologists consider these as some kind of a noise, because when they analyze the pressure variation, they will find minute, small variations there, and they attribute that to gravity waves. So for them, gravity waves is a source of noise. For us, of course, gravity waves is our bread and butter. So stable density stratification is the key to understand the atmospheric gravity waves. I think I already discussed all this. They arise due to the buoyancy. They are transverse waves. They can propagate vertically, horizontally. And an important property of these waves is they carry energy and momentum. That's very important. They are a very important agency for carrying this momentum energy. Waves do not involve material motion, but what is transported or what is transferred is the information. Is essentially it is the momentum and energy that are fed to the waves by some sources below, some agencies below, and these waves carry those momentum energy. These disturbances they propagate, they carry the momentum energy up into the atmosphere. These are some of the wavelengths and frequencies. So phase speeds of about up to 100 meters per second. 100 meters is very fast moving waves. So perhaps we encounter that very rarely. Typical phase speeds will normally lie in the range of 20 to 40 meters per second. 60 is not very uncommon. And waves with higher phase speeds, they tend to propagate to greater altitudes. Another important property of these waves is that they undergo Doppler shifting when they encounter background winds. So this is the intrinsic frequency, and it gets Doppler shifted, right? So once we have those primitive equations simplified, then we can do these dispersion relation calculations. And omega versus k, right? This is the kind of a dispersion relation. And here, in place of k, we have two zonal wave numbers, right? So because though it's 1D, but still we have waves propagating vertically up or down. So essentially it is 2D. So the k and m, they represent the zonal and the meridional wave numbers. And this is omega versus k relationship. Of course, we have to take into account the presence of the background wind there, where n represents the buoyancy frequency. Okay, so it's a square of the buoyancy frequency, and square is coming there in this term. N square plays a very important role, and that's where the atmospheric stability comes into the picture. I have to spend a little bit of time to explain what is this term here. What is shown here is gamma D and gamma. Gamma D represents the dry adiabatic lapse rate, and gamma is the environmental lapse rate. So what is dry adiabatic lapse rate? Any air mass which acquires heat from the surroundings, they expand and they become buoyant, and they move up vertically. They move up. As they move up, they keep on expanding, and they cool, expand, cool, and so on. This process continues till it loses all its external energy, whatever energy it had gathered. And because it is undergoing an adiabatic process, whereas the environment need not follow the. It can be at any particular temperature lapse. Whereas the air parcel, it's the rate at which temperature decreases when it undergoes the adiabatic. It always follows the dry adiabatic lapse rate, gamma d. So when you look at the difference between gamma d and gamma, that's where an expanding air mass, when it becomes lighter, then it will come down, and when the mass sinks and goes down, then it becomes warmer or lighter, it comes up. So this kind of an oscillation I explained below. So a warmer surroundings always leads to at the same time pressure always leads to a lighter kind of a scenario, whereas a colder environment, it leads to a denser scenario. So when you look at the rate at which the environment temperature, the ambient temperature varies, and compare that with the dry adiabatic lapse, you will immediately find that when the atmospheric lapse rate, say it's about temperature falls, say about 13 degrees per kilometer, then it's going to cool off very rapidly. But say your dry adiabatic lapse rate is only about, say, 10 degrees per kilometer, its temperature is not going to fall that steeply. So it's going to find itself always warmer than the surroundings. So a warmer, then it's lighter. So it's going to move up and up and up and up. It's not going to come back. So this is an unstable scenario. So for the stable scenario, suppose say you have an environmental lapse rate, say about 6 or 7 degrees per kilometer, and then you have the dry adiabatic lapse rate, say about 10 degrees per kilometer. Here, what happens is the environment is not going to decrease at a fast rate, environmental temperature, when compared to the partial lapse rate. So the partial will find itself all the time colder than the surroundings, and so heavier, and it will sink back. Okay. So this is the stable scenario. So I hope I made it clear what is the stable and what is the unstable scenario by just looking at n square term in the equation. So the above equation dispersion relation can be now recast as this in terms of m square versus remaining terms. So here, of course, the approximations where the curvature and the gradient terms, the du by dz and the d square u by dz square, those two terms have been ignored here for simplicity. So the m square relationship, m square versus the remaining terms, right? And the most important term is the first term. I think that's where we'll be spending some time discussing about what are the various scenarios, when m square becomes negative. When m square is positive, that means it's real and the waves can propagate. When m square is negative, then it's imaginary kind of a thing, and the waves can decay very fast. Okay? That means waves do not propagate in those regions where m square is negative, less than 0. And waves can propagate where m square is greater than 0. And n square is also important, right? So I was telling you this, we have to consider this term also, the difference between the dry and the environmental lapse rates. Okay. First, we have to see whether how fast or how the ambient temperature is varying. Then we can determine whether n square is going to be positive or negative at any location, at any height. Then we will come to m square. Here, n square is also there. If n square is negative, of course, m square is going to be negative. But the m square, if n square is positive, then we have to look at the other two terms, right? So what about c minus u whole square? This term, denominator term. When c approaches u, what happens is the m square term blows up, right? It approaches infinity. So the vertical wave number approaching infinity, that means the scale sizes in the vertical direction, the wavelengths are going to become shorter and shorter and shorter and shorter and shorter. Okay, and ultimately what happens is the waves will get absorbed there. Also, when c approaches u, the group speed of these waves they become smaller. That means the waves slow down whenever they approach the critical level. This is called a critical level. When c equal to u is called a critical level. So the wave slows down wherever it approaches a critical level, and slowing down of these waves can lead to damping or dissipation, and gradually wave energy and momentum will be taken away. Okay, so this we have to keep in mind. And m square is positive, no issue. The waves can propagate, no problem. So I think these two scenarios are nicely illustrated here. On this left-hand side, we have this m square greater than 0 scenario. And on this side, we have m square less than 0 scenario. And this is the growing wave amplitudes I was talking to you, in order to conserve the kinetic energy density of u dash square, because rho decreases with altitude. So u dash will have to decrease exponentially with altitude. And so this term is incorporated here in this e power 1 by 2h plus imz. And here it is e power 1 by 2h minus mz. So one is real and the other one is imaginary term. And you see these are all propagating solutions. On this side, we have the energy density decaying very steeply with altitude. Here you see this energy density is constant, and that's why the wave amplitudes are becoming greater and greater. Whereas in this m square less than scenario, the kinetic energy density is going to decrease very steeply with altitude, because this we have decaying solutions. No, they are not propagating solutions. M square less than 0. Okay, and so that's how it is. So we have to look at locations or altitudes where m square could be either positive or could be m square could be either positive or could be negative. So of course the ambient winds and temperatures, they determine whether the m square should be positive or negative. And of course waves other than gravity waves like tides and planetary waves, they have a large say on whether the m square has to be negative or positive. Okay, so it's not just a mean state of the atmosphere and then these waves are propagating and then we don't have anything there. It's not like that. Even we take about the mean state of the atmosphere, the stratosphere where the temperature is increasing with altitude, that is considered to be somewhat more stable than the mesosphere where the temperature is decreasing with altitude. Okay, so over that we have the presence of other waves that can determine whether we are going to have propagating or going to have a evanescent kind of a scenario for these small scale waves, right? Yes, I think these are all some typical examples of m square versus altitude. We have m square here. You see the positive throughout, and in this scenario, you see these are heights shown here is between 80 and 94 kilometers, and throughout 80 to 94 kilometers, you see m square is positive. No problems. We can have waves propagating throughout this region, but this we are not going to have it at every time. So, but rather it may be looking like this. We have m square profile again. So you see there is a dashed line. It divides the positive m square from the and the negative m square. So wherever we have positive m square, so here waves are going to have propagating solutions, and here when m square is less than 0, the waves would decay there. So what does it mean? Suppose so waves coming from below, wherever they find this kind of a negative m square region, they may undergo some kind of damping there. That means they will not be propagating kind of a wave. They may decay very fast, because I was telling you about the c minus u whole square term, right? They may approach a critical level, right? And that's why we have m square negative scenario there, or it could be n square contributing there, where temperature decreases much more steeply than the triadiabatic collapse rate at the ambient temperature. Okay? So these scenarios we have to keep in mind. When it comes to waves, different types of waves, you see. Why I am showing this particular picture is to show the importance of gravity waves high up in the atmosphere, say about 80, 90, 100 kilometers. See, the gravity wave amplitudes are increasing with velocity, right? Of course, we have a wide spectrum of waves, so it's not that it represents just one wave feature or wave scale. It represents multitude of wave scales, right? Whereas the planetary waves, they do not propagate. They may undergo critical level interaction. For example, in summer, they can be as low as say 40 or 45 kilometers. These planetary waves will just disappear. Whereas in the winter, these planetary waves can go up even up to 80 or 85 kilometer altitude. Okay, so that depends on the phase speed of the planetary waves and the background mean wind, right? Now, I think I have another 10 more minutes. I'll try to go fast now. As waves propagate without damping or dissipation, their amplitudes would be too large at higher altitudes. Imagine if there was no damping or dissipation, what kind of amplitudes you would have got there? 300, 400 meters per second. But we have only 30, 40 meters per second kind of phase speeds there. So, or U prime there. Dissipative processes, essentially eddy and molecular diffusion, and also could be radiative damping or thermal damping. So the wave breaking essentially results from the convective and shear instabilities. So we have a warmer, lighter air on colder, denser air. So I was telling you it's a stable scenario. Suppose if we have a colder, denser air over warmer, lighter air, that's an unstable scenario. Okay, it leads to convective instability. We can also have winds increasing very steeply with altitude, and these winds can induce kind of a instability into the medium. This sudden rise in wind speed, they can act as they can provide some kind of a free energy to the system. So we'll have another instability called shear instability, and these instabilities they can eat away energy and momentum very quickly. So wave breaking is a very, very important aspect, especially at altitudes that we are discussing, say 80, 90 kilometers or more. So we talk about convective overturning, okay? Like waves on a shore, when they reach large amplitudes, some kind of turning they undergo, right? So we can have similar kind of a turning, overturning we can have in the mesosphere as well. So that's just one example I'm telling. So these instabilities, they take away the energy and momentum. So these waves would damp away very quickly. Okay? If not for these instabilities I was telling you, you would have seen very large perturbation amplitudes there, but we don't see them at those altitudes. Okay, so both the dissipation and the wave breaking, they play an important role. Of course, there is a dispersion also, and that's a competition between the wave breaking and the dispersion, and some kind of non-linear scenario also might arise. I think I will talk about that. Maybe it is coming in one of the slides there. So another important thing is when these waves interact with the background wind. So what happens is when they decay, they deposit their energy and momentum into the mean state. So they try to accelerate the U bar. U bar is the mean state, whereas U prime is a perturbation. So they try to accelerate U bar towards their own speed, these waves. Okay? And of course, when when C reaches U bar, that's where the critical level happens. So till that level is reached, the waves would continue to accelerate the mean flow, accelerate or decelerate, again, depending on the direction. So this divergence of this zonal momentum flux or meridional horizontal momentum flux is what contributes to this kind of an acceleration into the. So if you write down a system of equations, this divergence of the horizontal momentum flux, the vertical divergence of the horizontal momentum flux, that feeds into the acceleration term. Okay. So mean flow acceleration, that was just explained, the waves would get slowed down and ultimately they would get absorbed. And these waves will be filtered out from the propagating spectrum of waves. So once those waves are filtered out, the rest of the waves, of course, they are going out. And gradually, one wave after another wave, and wherever they encounter this critical level, they will be filtered out. Okay, finally, another 10 minutes, last 10 minutes, I would like to spend some time on some of the observations that are reported about the internal bores, the theory, and what do we know about these internal bores, and what are the challenges. I just quickly run through these slides. Okay. Remote sensing of airglow emissions, so some of the very important observational tool to capture these wave events and bores and so on. So airglow is essentially it's a glow of air. Specific species like hydroxyl, sodium, and molecular oxygen and oxygen. They have excited states, and these excited states, when these molecules, excited atoms and molecules, when they relax to the ground state, they emit radiation. Okay, that radiation we call that as airglow. And energy can come from various types of chemical reactions taking place there. During the day, they are all photochemical reactions. Photochemistry, it provides energy to excite these species, whereas during nighttime, we have these exothermic chemical reactions that lead to the excess of chemical energy feeding those excited states, and then the species relax and they emit radiation. Okay. Small scale images with the CCD camera, they capture large to small scale features. And these atmospheric waves, when they propagate through the airglow region, they can cause variations in the airglow intensities, okay, through their density and temperature perturbations. Okay, they cause perturbations in densities and temperatures. And of course, through chemistry, these density temperature perturbations are going to drive the changes in the intensities. So by monitoring the airglow intensities across the sky, we'll be able to nicely keep track of those waves, right? So the dynamical features that have been reported so far are the quasi-monochromatic gravity waves, crests and troughs. These wave features seen as intensity variations, dark, bright bands of structures. We also seen frontal events like walls and bores, and we also seen small-scale instability features called ripples. So when, as I was telling you, when these large-scale waves, when they break, they feed energy to small-scale waves. And all-sky airglow imaging observations have revealed the presence of these small-scale waves as well. Because we have multiple heights, emissions coming from multiple heights, we examine the phase relations between the intensity variations in these species that can give information about how these waves propagate and whether they are evanescent or whether they are propagating, or whether we see presence of wave in one altitude, whereas we don't see them in other altitudes. So all these things can be studied, looking at the phase perturbations, the phase relations between the intensity perturbations. So I'll just show you a few examples of the kind of frontal events were reported. The first one was by Taylor et al. 1995. This was there was a follow-up study by Dewan and Pickard in 1998, who showed that this spectacular frontal event was actually, in fact, it was a mesospheric bore. So what you see here is the rushing up of a patch of airglow emitting region, and then you see that you see some kind of waves there following. So this is the front, and then the front travels and face lock to this front or the crests and troughs. Okay, so you have some kind of a complementary scenario. This is at a height of 97 kilometers, is 557 nanometer emission. This is at a height of 87 kilometers. There is a 10 kilometer separation. So what you see here is that in one case, so we have this dark patch, this propagating. Of course, there was a bright background here. This front separates the bright and the dark background region, bright and the dark regions. When it comes to OH thing, what you see is the sky is already black. The background is already black, but you have this bright emission feature that's now moving towards this region. And of course, again, we have these crests and troughs. So this was a spectacular frontal event, and Devon and Picard, they developed a simple two-layer based model, and based on hydraulic jump theory. So you have this. This is the bore, and they consider a frame of reference which is stationary with respect to the bore, and U0 is velocity with which the fluid is moving. Of course, it is relative to the bore. Actually, bore is moving with the speed of U0 like this, but here bore frame of reference is stationary. And then you have H0 and H1, and H1 is the depth in the region of bore, and is undisplaced depth U0. And using this theory, drawing an analogy from hydraulic jump, Devon and Pickard could demonstrate that what Taylor et al. Observed was indeed a mesospheric bore kind of thing, a bore in the mesosphere. Okay. So later, during the year 2001, they have another paper wherein they examined the wave steepening in a duct. Because I was telling you about the m square greater than 0 region. Those regions will act like a duct. And if you have a wind, a very strong wind blowing in that duct, they can undergo critical level interaction, and then they can accelerate some kind of background wind. And these regenerated disturbance, they can propagate like a bow. So initially we have wind blowing in this direction, and the bow propagating in the opposite direction. That's what the hydraulic jump also shows. Theory shows. So in 2001, they examined the wave steepening because you have a duct, no? So these waves can kind of undergo some kind of a overturn, okay? Some kind of a steepening, and they can produce some kind of a solitary structures. Even later research workers, they have suggested that we can have kind of a solitons there at in those regions where there is a nice duct, and these ducts running few hundreds of kilometers and maybe even thousands of kilometers. Okay. So this I was telling you about the temperature inversion here, temperature increase with altitude, and this is the ducting region. Okay, and you can have a bore propagating in that ducting region. Okay. And our observations will show that whether we are observing OH or this ONS, it is actually the 5577 emission or the broadband emission. So they will show up if we have a bore-like disturbance propagating through this temperature inversion region. Okay. So I was some scenarios, simplified, very simplified scenarios I have mentioned here. A temperature inversion with a peak between two airglow emission heights. Okay, can be there. And n square defines ducting region based on the temperature alone. The duct can be generated by wind as well. Okay. And so gravity of critical level interaction can force a wind that can trigger a bore to propagate in the opposite direction, similar to cold fronts, intruding into a stable layer in the lower troposphere. Once launched, the bore can travel a large distance to the duct, okay, till damping takes over. The duct can be suppressed where temperature and wind they are not favorable for its sustenance. Okay. There's another observation from Millstone Hill. There are also frontal events. They observed walls as well as bore-like features. And these are all wall-like features, and these are all bore-like features. So when it comes to bore, you'll find that following the front, there is always a face-locked crest and troughs will be seen there. Whereas in the kind of a wall event, you will see a large-scale feature, and that's it. It will just propagate. Maybe one or two wave crests following, and then that's it. They will be just propagating, and they will disappear. They will dissipate very quickly. This is another very important work recently carried out by Hozumi et al. They use satellite observations. So wherein they see bright as well as dark bores, right? Okay, and they explain their ideas in terms of where exactly the duct was located. The duct was located above the airglow layer or below the airglow layer. So accordingly, you will have this bright versus dark bore scenario. Okay. And very importantly, they brought out for the first time from the satellite observations. This is of the VISI instrument of the IMAP mission on board the International Space Station. and they brought out the geographical and seasonal variability of these mesospheric bores. I think we had our own work carried out in the year 2009, wherein we reported the bores from Tirunelveli. Okay, so you see these large extended fronts and followed by waves. These face-locked crests and troughs, and they'll be propagating this direction. So we found at that time that the winds were orthogonal, because when winds become important for the bore propagation is whether the winds blowing in the same direction or in the opposite direction, they become important. They blow in the same direction, then that can create some kind of a critical level interaction kind of thing. Whereas the bore propagating in the opposite, and the wind propagating in the opposite direction, that can force this kind of a bore scenario. So, but in many scenarios, we found that the winds were orthogonal many times. So perhaps we are looking at we need a thermal duct kind of a thing. We need a temperature inversion to explain the presence of these bores. And usually people use LiDAR observations. If you have on board, if you have co-located LiDAR, it gives you temperature and wind profile if it is a Doppler LiDAR. If we don't have LiDAR observations, then we have to depend on SABRE observations. It provides temperature profile in this particular region. But the SABRE, again, they are not continuous. Okay, they are kind of observations there. We don't have that many frequent passes, right? So we have to wait for another pass, and may not have simultaneous observation. So there are issues using SABRE observation. If you have an overhead pass, then you are lucky. But again, how well the overhead SABRE temperature profile would represent the background temperature, again, it's a big question mark. We really don't know. So, so there are issues. I think probably the last slide is going to talk about that. I think this is our recent observations, probably perhaps the last observational slide. I'll just show you what excitement we got looking at some of the I'll have to open that. So this is on 9th December 2018 when I was physically present there at Silchar. Okay, this is located in Assam, and I was looking at the observations, and then later on I and my student analyzed, and there's a lot of things happening on that night. A lot of things happening on that night, 9th December 2018. You see this in 5577, you see this kind of a frontal kind of a structure. It is just propagating, going up like this in this direction. At the same time, you see that crests and troughs, alternating crests and troughs, at least brighter crests you are able to see, and they are propagating in an orthogonal direction. Just they are going propagating like this, whereas this kind of a frontal structure is propagating in this direction. When it comes to OH, this is a hydroxyl emission at 87 kilometers. You see this kind of a dark patch, dark region of the sky. You see a very sharp front there. And they are traveling, and they are encompassing the whole sky, say about within 45 minutes or so. Okay. So I'll show once again. See this dark patch, which is just moving and just filling up the sky. And you don't see very clearly the crest and troughs, but when you examine the individual images carefully, you will see them. And of course, these are all people normally do subsequent differencing method. I have not done that here. And finally, this is on 11th of, you see something different here. You see this kind of a structure propagating in this direction. Okay, this is just anti-parallel to what was observed on 9th. Okay, this is very, very peculiar, because as according to Zumi et al., these bores, especially at low and mid latitudes, especially at mid latitudes, Silchar is not very far away from a mid latitude location. So we expect usually bores propagate from winter to summer, but here during this winter of 2018, we have bores propagating in anti-parallel directions. One bore is propagating towards southeast. That was on 11th December. Then whereas the bore on 9th December was propagating towards northwest, right? One day northwest propagation, other day southeast propagation. They are propagating in anti-parallel directions. Why? So that means the conditions were different on these two nights. Whereas on 9th, we also observed a gravity wave which is propagating towards northeast in the orthogonal to both of these bore propagation directions. So something very peculiar has been happening there on these two nights. Okay, I think this is the last slide and some concluding remarks and also some more challenges to understanding. I'm not sure whether I could go through. I could not go through a lot of literature on bores because of want of time. I restricted myself. I spent a lot of time on atmospheric waves and the presence of ducts, stable region, and because they're all very important concepts, so I thought I should spend more time on that, and because they all can explain the presence of bores. Still, the generation of bores is a very big question mark. I really don't know how bores are generated. But what we know here is once we have the duct, once we have a stable region, then we know that these bores can propagate through those stable regions. But exactly how the bores are generated, I think it's an open question still. Okay. So our observations reveal two bores observed in the same season propagate in opposite directions. So difficulty in assessing the nature of duct responsible for the bore propagation due to lack of collocated measurements. Probably because we don't have collocated temperatures or winds, at least for Silchar is concerned. We have for Kolhapur, we have a sky imager and we have a radar that can give information about winds, but for Silchar we don't have. And many of the sites, of course, they neither has LiDAR or have radar, so they have to depend on satellite temperature profile. So it's a lot of limitations there. Then the forcing mechanisms, as I was telling you, it's convective outflows considered to be a strong contender for tropospheric bores, but when it comes to mesospheric bores, we still don't know what role gravity waves play. It's still not clear. Analytical approaches in recent years try to bring in wave steepening effect by invoking solitary wave solutions. But the details of how the bore evolves and dissipates still, I think, they're only beginning to be understood. And finally, if gravity waves are considered to overturn and contribute to a bore or provide a forcing through its particular level of traction back and forth, then there is a need to identify the sources of gravity waves themselves. Because this is one of the fundamental problems on gravity wave physics. The source mechanisms, and the challenge lies in linking what we observe at say 80-90 kilometers to the sources lower below. So that's a big issue we are facing. So besides the possible role in bore generation, we need to understand the sources of, we need to identify sources of gravity waves themselves. I think I will stop here. I've taken some more time. Thank you once again, Professor Pallamraju, for giving me an opportunity, and also to all the other community. It's nice speaking to you. Okay.
Thank you very much. Guru Baran, it's been very nice talk, nice exposition to, I should say, a very nice tutorial in terms of waves. In the beginning, of course, cut down, substantially as I can. Even within the given time, you did a pretty nice job in introducing different types of waves, how they propagate, where they propagate, and the conditions. And towards the end, you showed very exciting results and that those open several interesting new ideas and new ways to look at the atmospheric dynamics. Yes. So it's nice, and I think we can take some questions. I think one of the questions is by Dr. R.P. Singh. He's saying, how challenging it is to measure these internal bores at the mesospheric heights using satellite-based observations. How frequent they are?
Yeah. Yes, I think as I was giving reference to that Hozumi et al. Paper, So, of course, there are going to be some kind of a snapshot observations because they are just passing by and they're quickly capturing just a snapshot. So, but they are covered almost all the globe and several degrees of latitudes and around the globe at different seasons they have covered. I think around 64. I'm not able to recall. Around 64 more observations they studied covering various latitudes, longitudes, and all that. Of course, if they are there, we are going to capture that, right? But boards themselves, earlier they were thought to be very uncommon, but now, but in later last few years, several years, 5 to 10 years, I think more and more board observations are coming back. If you have a camera on board a satellite, yes, and if the boards are there, yes, you'll be able to capture them, like what we do from ground. So similar way, you can capture those boards there.
Okay. There's a continuing question. Since mesospheric boards require a stable ducting layer supported by a temperature inversion or wind shear, what sort of instruments may be optimal for the satellite platform?
Any instruments will give you information about the temperatures and winds. They are the basic parameters that we need. And of course, from ground also, those instruments are needed. But unfortunately, we are yet to have a satellite, yet to have a mission where we can have all this together on one platform. We either have temperatures, we either have winds, or we have a camera there capturing all these bows. But unfortunately, we are yet to have a platform, a space platform, wherein all these instruments will be together. So I think, yes, temperatures, winds, and a camera capturing the various sky emissions. Because optical remote sensing is the only tool, as I see, to capture these emissions there. Right? Of course, there are noctilucent clouds also. Sometimes people have seen boards in the board-like structures with noctilucent clouds also. So maybe we'll be able to capture that.
But then that is in the higher latitudes because noctilucent clouds.
Correct. Higher latitudes.
But the measurements so far presented are mostly in the lower.
Mostly in mid latitudes. Mostly in the mid latitudes, mid and low latitudes. Correct. Yes.
Okay. Yes. Okay, I have a question by Deepu Chakrabarti. Relative spatial scale sizes of boards and inversion layers also important for group propagation.
Okay. Spatial scale sizes of boards
I think
and inversion layer. Yeah. For example, the boards can extend maybe because we have seen the boards covering the entire field of view is about 400-500 kilometers. It can even go beyond that also. And inversion layer, if you talk about, essentially it is the depth of the inversion layer is very important there. And then over what distances this inversion layer extends. No? So these two together will be definitely they will be important. Yes, the depth is important. Depth of the inversion layer is important, and it can so happen that we don't see the duct after a few hundred kilometers. The duct suddenly disappears. We don't have a stable layer there. Then these boards they just dissipate, or they may just disappear. By maybe they can even overturn, or even they may not even reach those altitudes as well.
Have you seen these two together? OH, and O1S showing boards.
Yes, from Tirunelveli, we have seen most of the times what we noticed was this complementarity signature. We don't see them. I don't know. Maybe the boards are somewhat at a lower altitude, so that complementarity signature, or maybe the one of the emissions is weak. So we need to go to a place where we need to have the background emission should be sufficiently strong, and then the duct should be placed somewhere. Ideally, the duct should be placed somewhere in between the O1S and the OH layer. Then we can have this kind of duct getting pushed up above and duct getting pushed down below, and we can have some kind of a complementarity signature. Right. But in even the three observations, we noticed that in out of these three board-like scenarios, only in one we're seeing this. It's appearing in both the cases. OH as well as 5577. The other two cases, one is definitely you don't see. The other one, we are not sure whether it is a bore or it is just a front-like structure. So it depends on where the duct is located. Whether it is located close to OH layer, then we may not see in 5577. If the duct is located close to 5577, we may not see in OH. Or duct is located well below OH, then we may not see in either of them.
Okay. What could be the reason for duct located much below OH layer? Because the temperature is
generally the temperature is decreasing with altitude. Then, as I was telling you, some of these waves, when they break, what they do is they accelerate and decelerate the background wave, and they also, when the waves damp or dissipate, they produce some kind of a localized heating there. And this heating can give rise to a local temperature inversion kind of a scenario. Instead of temperature decreasing, when waves break, the temperature can increase at certain altitudes. There can be a local, So, of course, the wave breaking is a main feature there to contribute to this kind of inversion and this kind of a duct-like scenario.
So there's a question by Sovan Saha. Is there any reported observations which found the Bohr atmospheric, Bohr at atmospheric altitudes, like 50 kilometers?
No. What I was telling you is essentially the latitudinal propagation is what I'm talking about. These Bohrs can propagate several hundreds of kilometers horizontally. Because once we have a duct, it's like a waveguide, no? So we have a waveguide, and then it exists. The Bohr can propagate as long as these waveguides are there. But as I was telling you, most of these waves, they get damped out. By the time you reach 100 kilometers, most of these small-scale waves, and they're all they get damped out. So, so you have only large-scale features like diurnal tide and all that at very high altitudes, like 250 kilometers or so. So, as far as I understand, I don't think there is any Bohr-like scenario reported for the thermosphere.
Yeah, there's a follow-up question by R.P. Singh. And the nonlinear interaction between gravity waves and tides is known for the origin of the inversion layer. Is this both show any seasonal variation?
I think this Hozumi et al. Paper, they found strong seasonal variations in the occurrence of Bohrs, and they attribute that to the presence of tides, especially the nonlinear interaction between the tides and the gravity waves. Okay, and they were able to explain very nicely why tides could play an important role there, explaining the seasonal variations in Bohr population. But when it comes to low latitudes, unfortunately, we don't have measurements, and unfortunately, our observations are restricted to, say, only mostly winter, sometimes during March, April, and maybe October, September. So other times are all monsoon and clouds and kind of a thing. So for low latitudes, at least for our Indian sector, we are able to get any. But earlier observations that do indicate we have shown some seasonal dependence for gravity waves based on several years of observations. Because Bohrs were thought to be so rare, so maybe now we should look back and see how frequently we have been observing Bohrs, and maybe then we can bring out some. But it's a very elaborate exercise. It's carrying out analysis of Bohrs is not so straightforward. Lots of things go into the analysis. So now with all these machine learning and all that, artificial intelligence and all that, hopefully we'll come out of it, and we'll find a way out to do quick analysis and get results.
Yeah. So has there been any reports? Do you observe them after any convective activities? Prior to this, prior to the Bohr events, of course.
Yes, we ourselves had in that 2009 paper when we observed a very strong, spectacular Bohr-like event from Tirunelveli. We noticed convective activity over Indonesia, and so perhaps that could have triggered some kind of a Bohr-like thing there at those latitudes, at those locations. But unless and until we do some kind of a ray tracing, because that's a very, very important aspect. And unless we model the ambient, the background temperature that means not accurately, to somewhat closer to the realistic sense, only then I think we'll be able to make some progress in modeling and all that kind of thing. as till then, I think this is all open-ended problems.
Yeah. Is a continuing on with the stability requirement. RP Singh is asking, is there any stability requirement for temperature inversion layer for the occurrence of these boards?
Yes, the fact that the temperature is increasing with altitude, no? That itself suggests that the region is stable. So if the temperature increases, we have to look into the n square profile. No? N square, I showed you how fast that ambient lapse rate varies with altitude. So yes, for temperature inversion, for stability, you need the temperature inversion there. Of course, without temperature inversion, you don't expect a stable layer there, because it's one of the reasons, right?
Okay. In one of the examples that you showed, you said that the winds were orthogonal. In that.
Yeah.
So was it an inference, or you had independent measurements to say that? Because
as far as Tirunelveli was concerned, we had an MF radar. Even for Kolhapur also, we have an MF radar. So if we have a co-located wind, then you measure the wind speed and wind direction at that time. If they are orthogonal, then you take the component. No? The component along the bore propagation direction will be 0. They are exactly orthogonal. So that means that C minus U, that dispersion relation U bar is not going to play any role there. So that is what an important thing is. But there are reports that people have shown that there could be U bar, which is blowing in the wind was blowing in the anti-parallel direction. That could have generated, could have contributed to not only a duct, but could also contribute to a driven bore-like scenario. There are papers. There are other reports that suggest that at the time of bore, we are seeing wind, orthogonal wind. And then we just come out of that. We don't have to explain the role of winds there. As long as you see winds blowing in the opposite, because we don't know what winds prevail where the bores are generated. Where smoke might have generated way behind us. We really don't know what conditions would have prevailed there. But at least over our side, we know the winds are orthogonal, so no problem.
Okay, there are. I think we had a lot of nice discussion. If there are no more questions, let me thank Professor Gurubaran for this very nice and lucid talk on a very interesting, observations, which again tell us more about the atmospheric dynamics and structure, and we are learning more and more by these newer measurements. And I take this opportunity to thank Professor Gurubaran again on behalf of PRL, and I would also like to thank the colleagues of IIG who may be joining us on this colloquium. I would like to say that every Wednesday we have this colloquium, so I'll invite all of the colleagues at IIG and other viewers and all my colleagues to please tune in on Wednesdays. Next, we continue on with this excellent colloquium series on knowing various things from different fields. We now come down to the surface in the next week's colloquium, which will be by Professor Vikrant Jain from IIT Gandhinagar. He's going to talk to us on the rivers in the Anthropocene, an assessment of Indian rivers. And I thank you all for joining this week's colloquium, and I would like to look forward to see you all in the next week's colloquium also. Thank you, Gurubaran, once again, and thank you to all the people who are joining on this webinar. Thank you, stay safe, and see you next week. Bye-bye.